Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Welcome to this session on data intensive computing. I'm Peter Lee, and we have three talks in this session, and all pertaining to the question of how one arranges the computing for eScience. And so our first speaker is Randy Bryant, who's the Dean of Computer Science here at Carnegie Mellon, and he's thought actually quite deeply about the question of the architecture of computing for eScience. So, Randy?
I kind of gave myself a dope slap this morning for coming up with the title Applying Google-Style Computing to eScience at a workshop sponsored by Microsoft. But there's actually a reason to that. It's not just a random attribution. So, of course, a lot of eScience is all about big data, very large data sources, and not just in scale, but with the desire to do a lot of sophisticated computation over it. And of course, that's in science, but also in the business world, in the medical world, and all over. And so there's many different fields that are really interested. And in fact, the search domain, web search, has really been a big driver for this. So when I say Google style, I mean a couple.
You say Google style?
I do. Tony, I said that I gave myself a dope slap this morning, though. So, but I mean two things. One is a style of building computer systems on a scale that's sort of unprecedented. Of course, we don't really honestly expect to build computer systems of this scale for our rather paltry eScience problems, but still the idea of assembling very, very large systems out of essentially commodity parts. And so, in fact, Google used to be very secretive about it, but recently you can get YouTube videos of tours of the inside of their data centers. So they build them in a modular way. I think Microsoft does this now too, of just filling up shipping containers full of machines, and then piling them into big warehouses, plumbing them with a lot of electricity and a lot of cold water, and letting them run. Hooked together by relatively low performance communication compared to, say, what you'd build in a really large supercomputing system. So these things are engineered very carefully, but yet they're also engineered to be very price effective. And one attribute of that is that they break all the time. Every component fails all the time, and the systems are then engineered using software-based fault tolerance to be able to continue running in the face of repeated component failures. The other thing is the MapReduce programming model, or the idea that rather than being down at the sort of bare metal writing code, that you're up at a higher level thinking in a sort of data parallel way about what operations you want to perform on the data without so much concern of where is that data located, how do I schedule the tasks, what do I do when one of the files disappears because a disk fails. And so that's what I mean by Google style, is a style of building computer systems and a style of programming them. So this is an area that I've been very interested in for several years, so let me talk some about the general properties and principles of it. Of course, we know the driving factor behind why there's so much data out there, at least one of the reasons, is the tremendous progress in magnetic storage technology, so that you can go off and buy a multi-terabyte disk drives for less than 10 cents per gigabyte. And in fact, over the years I've given this talk, I have to keep going back to Amazon to get the latest price on a disk drive because it keeps dropping. So that's the good news, is that the data storage is essentially free in terms of just the raw capacity. The bad news is that the transfer rate of getting information on and off of disks or getting it across even a local area network is a much bigger problem. So a terabyte is nothing in terms of buying a disk drive to store it, but if you just want to copy or even read through all the data on a disk drive, it takes several hours. And if you want to copy it from one machine to another, or even worse, from one end of the country to the other, you're talking hours, days, possibly to do the transfer. So what it means is that you can build up these very large data sets, but then they kind of get stuck in one place. And even if you want to then in one computation do something that will access, say, a terabyte's worth of data, it's actually a fairly challenging task. So for example, imagine something you want to do where you have a terabyte-sized data set and you just want to scan through it and do some very rudimentary task. Find some label in there. Compute the average of a group of numbers. Well, the only way you're going to be able to do that in a reasonable amount of time is to distribute that data over many disk drives, have all of them working with their own processors, working locally, and then communicating over some decent but not necessarily super-duper local area internet. And so that's why you move to these systems that have shipping containers full of processors and disks working together, and why that, the motivation behind that style of system building. So we call these a data-intensive supercomputer or data-intensive scalable computer. It's mostly an acronym in search of a name. But the idea of it is, again, to focus on a very large-scale computer systems, but the real purpose in life is to be able to work with very large-scale data and do interesting computation over that data, not just store it and retrieve it, but be able to apply various analytic tasks to it. So my sort of 4 characteristics of that is, A, the main issue is sort of the moniker would be terabytes, not teraflops, that it's really about how much storage you can maintain and make good use of. The other is a programming model where you're not thinking about the machine as much as the problems that you're trying to solve. An ability to interact with it directly rather than, say, a traditional supercomputer where it's a very batch-oriented processing. And then finally, from a system perspective, having a system that's engineered so that you can withstand the continuous failures that would happen at the hardware level and possibly the software level, and not have to bring down the whole machine. So just as to go through some of those attributes in a little more detail, the idea of in most large-scale computing systems, it's somebody else's problem where the data is going to be held and how to get it into the system in order to do the computation. But with these scale data sets we're dealing with, that's really not feasible to move it into the system. And so this was one of Jim Gray's things. It's easier to move the code to the data than the data to the code. So what you'd really like to do is have this data all collected and held together and managed with all the right stuff and continuously updated and handled. But then when you want to do some analytic task, you'd then ship a program over to this system, run it on there. It might be fairly sophisticated, what you're trying to do with it, but really do the computation on site. As I mentioned, the idea of having a programming model that is not directly thinking about the raw hardware, which is the way most programming of, say, based on MPI is done, where you really think about, I've got 64 processors, I need to partition my simulation domain into 64 regions and run them each in parallel on these different processors. But rather you think about, I've got a bunch of data, they're in a bunch of files, I want to collectively do some computation over all of that data. And then there's a runtime system that deals with issues about how to manage the tasks, how to distribute the data, how to locate things, how to deal with failures. As I mentioned, this reliability is sort of key to being able to scale a system up to a really large size and not have it cost hundreds of millions of dollars just to build one system like you'd see in a supercomputer. So for being able to use this, there's a growing body of open source software the project called Hadoop, which has largely been supported by Yahoo, in fact, is available, and it provides a basic parallel file system and a MapReduce programming framework. And so there's increasing interest in Hadoop and a large community of people using it these days. So let's focus on one particular area of eScience where we have some experience, and that's in dealing with astronomy. And so in astronomy, there's sort of two main types of data. One is sky surveys, which is, of course, what Jim Gray got started with Alex, and starting with the Sloan survey, I believe, where there's just huge amounts of astronomical data being collected, and Jim really demonstrated that this brings in a whole new possibility of computer scientists working with domain scientists to make this data available and do interesting things with it. Another end of it is the data that comes out of supercomputers. They spew out tons and tons of data, and so in particular here at Carnegie Mellon we have a cosmology center called the McWilliams Center that runs very large simulations of the evolution of the universe. And then after that, they've got a lot of data generated that they want to analyze and see what's going on. So we've started a project that we call Astro, and it involves a few people, Julio Lopez, who's back there, Eugene Fink, and graduate student Bin Fu, where we're using some of this astronomy data as a driver for exploring some of the more of the computer science issues behind this data-intensive computing. So in particular, using the Hadoop framework to do the types of computational tasks that astronomers want to be able to do to their data, and how do sort of scientific algorithms then scale up and fit within a MapReduce framework. And also some interest in the more persistent storage. In addition to Hadoop providing a programming framework, there's an increasing interest in what we'll call scalable tables. So a scalable table is sort of layering some aspects of database functionality on top of a parallel file system. So it's not a true database. You can't do arbitrary relational queries, but it provides some of the key attributes that people associate with databases, that the data are organized in schemas, there's some structure to it, there's simple queries where you can access individual parts of it, and some amounts of transaction and atomicity in how you do the updating, without, while sort of always thinking about what can be done on a very large scale using a distributed fault-tolerant file system, and therefore backing off from some of the full-fledged attributes of relational databases. We've gotten funding that allows us to do this work and also to build our own cluster, not a huge cluster, but a big enough one that we've been developing. So this has been funded by Google, partly, and the Moore Foundation. We've been working somewhat with people at University of Washington as well. So just as an example of one of the projects that we've worked on, the work known as halo finding is you're given a bunch of particles, maybe stars, each of which has its own position in X, Y, Z space, and it has some identifier associated with it. And now what we're trying to do is merge these into regions based on some radius of what's considered nearby. And then each particle then gets assigned an ID identifying which region it's part of. So this is, of course, a kind for which there's been a lot of work, but how can we do this using MapReduce? So in the particular implementation, it's sort of what you'd expect, that you start with just the raw data, which is files of the individual objects labeled with their XYZ coordinates, and then you use a map to then distribute those into regions. So you partition all of space into a set of overlapping regions and then map each particle into one or more regions in which it's located. And so that's done using one MapReduce step. And then we have these regions. Now we can locally, in a sort of massively parallel way, just apply region finding or halo finding to those using the so-called friends of friends algorithm that just sort of greedily clusters things together. And so for each of those regions, using just the normal sequential code for that, we identify those. And then we now have a bunch of regions, each of which has labeled halos. And now what we have to do is some amount of coalescing of the halos that split across multiple regions. But there's few enough of those, and it's a simple enough task that we can just do that using a single union find running on a sequential machine. So we've successfully implemented this and applied it to some fairly large-scale data sets, and it's been a demonstration that at least this type of task is fairly suitable for a MapReduce computing framework. So just to finish up then, the sort of idea we've been looking at then is this idea of a very large-scale data-intensive computing. And in fact, it's interesting. This morning, of course, the discussion, a lot of it was building on Jim Gray's legacy. But I think one of the parts that Jim Gray, unfortunately, hasn't been able to partake in is this idea that it's not just the data that we want to get, but we also want to do computation that is distributed and spread over these very large data sets. And so we need to go beyond sort of a traditional database view of the world to one where we're merging on top of the data storage and issues is how do we then map very large-scale distributed computing onto that data. And that's where we're taking this particular project, and I think it will have a lot of importance in the domain of eScience. So, thank you. Yes?
You mentioned about these new sorts of databases and about the cook-down functionality. Have you come across any examples where that cook-down functionality caused you problems, that made it more difficult for you to solve the problem, or it cost you in time?
I'll let Julio talk about that.
So for that type of applications, many applications in eScience, you need things like transactions and so on. So actually, these sort of boiled down databases with fewer features are actually perfect for this type of problem. We're exploring it, and we could at some point find solutions like we want to do things like join between two data sets, and then you have to run everything at the application level. Other than that, it's pretty great.
I think the main thing is the open source implementations of these tables are still only now getting to be good enough to be serious contenders for real scientists to be using. They're pretty crafty up till even a year ago.
Well, wait a second. MapReduce is join. The basic MapReduce operation is sort everything and stick it together.
Right. Not exactly. I mean, it's a restricted type.
No, you can express any type of join. In fact, there's papers that basically you can express any database computation.
You can express, not efficiently.
Right. But the point is, there's no such thing as an efficient relational database over billions of objects. Right? So,
okay, I'm not going to argue for the Vertica people, but the Vertica people will argue.
Well, and the Vertica people are being careful in what they say.
Any other questions? That was good. That was fun.